Welcome to Calc 3. This is section 13.6, triple integrals and volumes. So in the previous sections, we were talking about double integrals, where we were looking at the area under a curve, or excuse me, the area under a surface. So we took a surface and we looked at the area of rectangular solids, the volume of rectangular solids, where we had the base caps were little double integrals where we use dy dx as the base of, or the area of the top of the rectangles, and the function f of x, y gave us the height of the rectangles. When we're looking at triple integrals and we have some sort of region, some sort of domain D, we're looking for the volume of that domain. So we break up into small cubes where we have dx, dy, and dz as representing the area of tiny cubes, and we essentially build up the volume of the solid D with those small cubes. So let's look at an example here. So let's suppose that we have two functions, two surfaces, f1 and f2. So let's let f1 be the lower surface and f2 be the upper surface. f1 is sine of x times cosine y, and f2 of x is equal to cosine x times sine of y plus 2. And we're looking over the region R, which is defined by a triangular vertex with vertices 0, 0. We have vertices 0, pi, and pi 0 and pi, which is roughly here. So we're looking for the volume of the solid roughly over this triangle. So if we were to sketch out the triangle in the xy plane here shown, and we were looking at the volume of the shape in roughly this region covered by this kind of triangular segment here. We're looking about the volume between those two pieces. We need to set up our double integral. So just like in Calc 1, when we were looking for the volume between two curves, we can set up our integral the same way in Calc 3, where we look at the volume between two surfaces. So recall back in Calc 1, we looked at the volume of the upper curve minus the area, the function of the upper curve minus the function of the lower curve dx on the interval a to b. So here we do the same sort of thing. We look at the area, the double integral of the region, where we take the upper curve minus the lower curve times dA. So here we have the double integral from 0 to pi. We can describe the region as 0 to x, 0 to pi, of cosine of x, sine of y, plus 2, minus sine of x cosine of y as our lower curve, dy dx. And so to make clear where this region came from, if we think about what the triangle looks like, since we're looking at our bounds from 0 to 0, and it goes along the line, this line here is line y equals x. If we're looking at our, it's a little bit obnoxious. If we're looking at our lines, this line here is y equals x. We're looking at our, making our rectangles as we build up our triangles. We're building from y equals 0 to y equals x as our lower rectangles, and we're building from 0 to pi. So as we're building this function, this is an easy integral to solve. So what we can think of this is that these actually are z values. So this is like a z upper, and this is a z lower. So we could have set up this integral as the integral from 0 to pi, 0 to x, z lower, and z upper of 1 dz dy dx And this is where we come into play with the triple integral. And this is by the fundamental theorem of calculus. If we were to evaluate with respect to z, we would get z upper minus z lower as the inside piece. So in essence, we've built up our triple integral. And so this is where we define the idea of the volume. So here a definition for volume. For a triple integral, we have that we define the volume to be v is equal to the triple integral over some domain d of 1 with respect to dv, where d is a closed bounded region. And it's this domain that we care about. So this domain, just like the regions we had before, with our double integral, d is your closed bounded domain. And so this volume, you want to build up your example. And so from here, this double integral that we solved earlier, or that we set up earlier, is easy to solve. It's an easy integration problem to solve. So let's look at another example here. So let's let T represent the temperature in an object with points within a particular domain. And let's find the hypervolume. So let's build up the volume to a fourth dimension of the temperature as a function of location. So this would be as if we had a three-dimensional space, x, y, z, representing a room, and we looked at the temperature as a function of the points in that room. If the domain of the object was represented by x, y, z, such that we had a plane 2x plus 3y plus z equals 6. So we had some room with a plane within that room, and we were looking where all those variables were all positive. So we're looking in the first octant. And we also wanted the temperature function to be equal to 2x. So we have several conditions here. So we have our plane as our domain. So we're inside of our room. We're looking for the temperature function along that domain, and we have our temperature function is equal to 2x. So what we do know here is that we can set up our function such that z is equal to 6 minus 2x minus 3y. And this is just by rearranging this piece here. If we rearrange this for z, then we get an upper bound for z, because we have a lower bound for z. We know that z's lower bound is 0. So we know that z is bounded below by 0 and above by 6 minus 2x minus 3y. And if z is bounded above by this, then when we smash z down onto the xy plane, so if z equals 0, then when this is true, 0 equals 6 minus 2x minus 3y, then this implies that y equals 2 minus 2/3 x, solving this function for y. This is what happens if we take our z function and we're looking to see where the intersection of the two bounds is. Then we get a bound for y. So this means that y, our lower bound for y is 0, and our upper bound for y is 2 minus 2/3 x. We can do the same thing for y. If y equals 0, then 0 equals 2 minus 2/3 x. This implies that our upper bound for x has to be 3. So x equals 0 to 3 as its bounds. So now we can set up our integral. So our integral is now set up as 0 to 3, 0 to 2 minus 2/3 x, and 0 to 6 minus 2x minus 3y of 2x dz dy dx. And this is a nice problem to solve, because with the first variable, it's just a function of z. So we get 0 to 3, 0 to 2 minus 2/3 x, times 2x, 6 minus 2x minus 3y. And continuing on dy dx, we get 0 to 3 of 12x minus 4x squared minus 6xy dy dx. So let's drop the y integral, 0 to 2 minus 2/3 x. And as we can see, this is an easy polynomial to solve. So we get 0 to 3 of 12xy. Let's just go ahead and drop in the 2 minus 2/3 x minus 4x squared, 2 minus 2/3 x minus, and then we have 3x, 2 minus 2/3 x quantity squared with respect to x. We can simplify this out and then do the integral and solve that, and we get a value of 9. So this is the hypervolume of the temperature of that surface along that plane, given that the temperature is equal to 2x on that surface. Let's do one more problem. So let's describe the region of integration and solve this integral. So our integral is 0 to 1, 0 to x, 0 to x plus y of the function x plus y plus z, dz, dy, dx. Just as in the previous problem, we can think of this as some function t of x, y, z. So this is some hypersurface that we're describing. And so you can also think of this as a density function, the density in space. This is used in various application problems as well. So if we think about this projection, so if we're looking in the z plane, we're projecting onto the x, y plane. So in the z plane, we're looking down and we say z goes from 0 to x plus y. So if we think of z goes from the 0 plane, z equals 0 to z equals x plus y, this looks like the edge of a triangle. And then it's sometimes easier to build it from below. So let's look at the dx dy plane. So if x goes from 0 to 1, so if we're looking at the xy plane, here's our x, here's our y. X goes from 0 to 1, y goes from 0 to the line y equals x. So we're looking at this shaded region. And then z is building up from the line z equals 0. This bottom plane here to the plane x plus y. So we've got kind of this triangular region here, this sort of quadrant, this sort of kind of triangular solid in the plane here. So when we project it down, we see we've got this kind of corner here, and then we project it down. So that's essentially kind of what's going on here. So as we solve this integral, we see that we have 0 to 1, 0 to x, xz plus yz plus 1/2 z squared evaluated from 0 to x plus y dy dx. So this gives us 0 to 1, 0 to x. We get x plus y squared. We factor out the z here and drop an x plus y plus 1/2 x plus y squared. Oops. Dy dx, little simplification, 0 to 1, 0 to x, 3/2 quantity x plus y squared dy dx. This is a nice little u substitution. We can let u equal x plus y. So if u equals x plus y, du equals dx, or excuse me, dy with respect to y. And so then we have 3/2 u squared. And so if we're integrating this with respect to u, this just becomes 1/2 u cubed. So then we get the integral from 0 to 1 of 1/2 x plus y cubed evaluated from 0 to x dx. And here remember that we're doing with respect to y. So we get 0 to 1 of 1/2 2x cubed dx. So this is 2 cubed, so 2 cubed is 8, divided by 2 is 4. So we have 4x cubed, evaluated from 0 to 1, dx. So x to the 4th over 4 is just x to the 4th, evaluated from 0 to 1. Should give us 1. Except for I dropped the y equals 0. So let's go back and take out here. Let's go back and double check our. So we dropped in x equals y equals x, and then we negated this piece here, x cubed dx. It's important to do all the steps in the fundamental theorem of calculus. And so then we have the integral of 4x cubed minus the integral of 1/2 x cubed dx. And this gives us 1 minus 1/4, or excuse me, 1 minus 1/8, which gives us 7/8 as our final answer. So the second video in this section will have 2 more examples. As always, if you have any questions, please let me know.